Swayam Prabha. Digital India. Educated India.
Now, let us go about computing the angle change. Okay. Now, let us say I have a coordinate system Ex, Ey, Ez, and I have this body in the reference, a potato, this reference configuration. I have the same body in the current which did this is the current configuration. I take two line elements 1 and 2. Let us say this is B and let us say this is A vector, okay, at this point. Okay. Now, this point will map on to some point here in the current configuration, that A vector will get mapped on to some A vector here, small a vector here, and the B vector will get mapped on to some B vector, small b vector here. Okay. Now, let us say initially the angle measured from A to B is theta ref, and let us say the angle measured from B to A in the current configuration is theta current. Okay. Here I measure the angle from B to A, here also I measure the angle from B to A, here the angle is theta ref and here the angle is theta current. Now, I want to find what is gamma, which is theta current minus theta ref, that is a change in angle I want to find. Okay. Gamma is nothing but the change in angle between A and B. So, we will write it as gamma A B. Okay. So, that is a change in angle between A and B. Now, how do you find the angle between two direct line segments? I can use the dot product to find the angle between two direct line segments. In particular, norm of A will be equal to norm of B equal to 1, because they are dotted line segments along that direction. Okay. So, the norm of A and norm of B would be 1, then cos theta ref would be A dotted with B. Okay. Similarly, cos of theta current would be small a dotted with B divided by norm of A and norm of B. Okay. Now, from our definition of deformation gradient, you know that this is a straight line maps on to a straight line. Okay. So, what does the deformation gradient do? It maps small a to capital A like this, right. That is the mapping that we saw coming from our definition of deformation gradient. Dou x by dou psi is capital A, dou small x by dou psi is small a, okay. Because they are straight lines, you know that we saw in the last class that dou x by dou psi will be capital A, dou x by dou psi will be small a, and small a need not be a unit vector, because f is not going to preserve the lengths. F is a matrix which will change the lengths of the vectors if the length changes actually in the deformation process. Okay. So, that is why I am dividing it by norm of A and norm of B. Okay. So, this will be nothing but f times A dotted with f times B divided by norm of f A times norm of F B. This I can write it as F transpose F A daughter with B divided by norm of this is again F transpose F A daughter with A square root F transpose F B daughter with B square root. Okay. What we saw, F transpose F was C. So, cos of theta current would be C times A daughter with B divided by square root of C times A daughter with A times square root of C times B daughter with B. Okay. So, that is the current angle between A and B. Okay. What am I interested in? I am interested in finding the gamma AB. Now, I know what is the current angle, I know what is the reference angle. So, how do I go about computing gamma AB? I have to take the cos of the sine of gamma AB. Okay. We define gamma AB as theta current minus theta reference. Okay. So, theta current would be theta reference, this will imply theta current would be theta reference plus gamma A comma B, and let us take cos of theta current. Cos of theta current would be cos of theta ref plus gamma A comma B, that will be cos of theta ref into cos of gamma A comma B minus sine of theta ref into sine of gamma A comma B. Okay. Now, what we know is, we know cos of theta ref, but if gamma A B is small, that is less than 2 degrees, say less than 2 degrees, say, then what can I say? Cos of gamma A B is close to, what will be cos of gamma A B? For a small values of cos, it will be close to 1. Okay. So, this will be nothing but, so cos of theta current would be cos of theta ref minus sine of theta ref and gamma A comma B. Okay. So, this will imply gamma A comma B is nothing but cos of theta current minus cos of theta ref divided by sine of theta ref. Okay. So, now let us substitute for all these things. So, gamma A B is, from the previous page, you know that cos of theta current is given by this expression. Okay. Let us substitute that in here. So, this will be C times A daughter with B divided by square root of C times A daughter with A multiplied by square root of C times B daughter with B, that is theta current, minus cos theta ref is A daughter with B into 1 by sin theta ref. Okay. Now, you know that I can approximate this as 1 plus 2 epsilon for C, and that acted upon by A dotted with B, and denominator would be again 1 plus 2 epsilon A dot with A whole power of into 1 plus 2 epsilon B dot with B the whole power of, okay, minus A dot with B the whole multiplied by 1 by sine of theta ref. Okay. I do the same trick that I did for the change in the length. Okay. So, let us continue. So, you have gamma A B given as, this is under the assumption that if components of H is of order 10 power 3 or less. Okay. We already made the assumption here that the change in angle is small, which means the components of H has to be small. Okay. So, that is with this assumption only we are working throughout in this lecture. So, basically this will be A dot with B plus 2 times epsilon A dot with B divided by 1 plus 2 times epsilon A dot with A square root 1 plus 2 epsilon B dot with B minus A dot with B the whole divided 1 by sine theta ref. Okay. Now, what we can see is this is of order 10 power minus 3, this is of order 10 power minus 3, and this is also of order 10 power minus 3. So, 1 plus a square root of a small number, this entire thing I can approximate it as 1, and this entire thing I can approximate it as 1, because that is not significant. When I take it to the numerator, it will be again 1 plus a small number, and I am multiplying a small number with a further small number. So, I can approximate this as 1. Okay. Then what happens is gamma A comma B would approximate to A dot with B plus 2 times epsilon A dot with B minus A dot with B into 1 by sine theta ref. This is equal to 1 by sine theta ref 2 times epsilon A dot with B. Okay. So, the change in angle, therefore, change in angle between two directed line segments A and B is given by gamma A comma B, that will be 2 times epsilon A dot with B divided by sine of theta ref. Okay. That is an important expression that you should remember. Now, let us say A dot with B was 0. Let us say A dot with B is 0. What can you say about A and B? If A dot with B is 0, what can you say about A and B? You can say that the angle between A and B theta ref is pi by 2 or 90 degrees right. Okay. Then what is sin pi by 2 or sin 90? It is 1. Okay. That is why gamma between x and y axis, that is between Ex and Ey, is given by 2 times epsilon xy. How is this xy? Because you have 2 times epsilon Ex dot with Ey. This is nothing but the xy component of the corresponding strain tensor. Okay. We saw how to find the components of this tensor. So, this from that definition becomes 2 times epsilon xy. Okay. So, the change in angle is twice the strain tensor, the corresponding component of the strain tensor. Okay. Now, let us understand the meaning of different components of the strain tensor. Okay. Now, you have strain tensor given by epsilon xx, epsilon xy, epsilon xz. It is a symmetric tensor. So, I will write it as epsilon xy, yy, epsilon yz, epsilon xz, epsilon yz and epsilon zz. You found that epsilon of A, that is change in length by original length along a direction A, is given by epsilon A dot with A, and you found that gamma between A and B is given by 2 times epsilon A dot with B divided by sine of the angle between A and B. Okay. Now, what from here, if I take A as, if A is Ex or Ey or Ez, what do you get? You get the corresponding diagonal terms of this strain tensor. So, this diagonal terms represent the change in length by original length along the coordinate directions. Okay. It represents the change in length by original length along the coordinate directions. Okay. Now, what does this off diagonal terms tell you? These off diagonal terms tells us that it will be 1/2 of the angle change between the coordinate directions. Okay. The coordinate directions are mutually orthogonal. So, sin theta ref is 1, and if A is that and B is given by again Ex, Ey, Ez, then 2 times gamma Ex, Ey would be 2 times epsilon Ex dot with Ey. Okay. Now, this in most of the textbooks in elasticity, what will happen is they will say this angle change to be your gamma xy. Okay. And the strain in some books would be written as, the strain tensor would be written as epsilon xx, gamma xy, gamma xz, gamma xy, epsilon yy, gamma yz, gamma xz, gamma yz, epsilon zz. Okay. Where this is not a tensor any longer, okay, because it does not comes from a proper tensor calculus or tensor algebra. Okay. This is not equal to 1/2 H plus H transpose like what we defined. Okay. This is not a tensor, second order tensor, it is not a second order tensor. So, the transformation rules for this will be different. We did not want to take that approach, and hence we are defining it as strain as a second order tensor and it has 1/2 of gradient of u plus gradient of u transpose. In particular, you will find that in this approach epsilon xx would be given as dou u x by dou x, just like what we got when you do half of h plus h transpose, but gamma xy would be dou u x by dou y plus dou u y by dou x, whereas epsilon xy would be 1/2 of dou u x by dou y plus dou u y by dou x. Okay. This half that we have here, this half that we have here and we have here is what makes this a second order tensor. This is a second order tensor. Okay. And this is not there here, and hence you got the 2 in here, and hence you got a 2 in here. Okay. In gamma xy that half is missing, hence this 2 will not be there when you use this as a strain tensor, strain matrix. Okay. That is not a second order tensor, it is a strain matrix. Okay. So, you have to understand that there will be differences in the notation between the textbooks, but you should not be confused by that. Okay. So, we are following a tensorial approach, and hence all our strain and stress are tensors and will transform like a second order tensor. The next class we will see how the strain transforms into changes in coordinate basis, okay, because these components are related to the coordinate basis, right. These components are related to the coordinate basis. We understood that this is the change in length by original length along a coordinate direction, and this is the change in angle between the coordinate directions. So, if my coordinate system changes, these values will change. So, how does it change? We will see in the next class, and that will conclude our discussion on strains. Okay. Thank you.